Let's review isomers, what we know about them. Isomers are compounds that have the same molecular formula, but they are different in some way. And we have talked about constitutional isomers and stereoisomers. Constitutional isomers have a different connectivity of atoms. So 2-methylpentane and 2,3-dimethylpentane both have the formula 1, 2, 3, C6H14, yet they are not the same. They are not connected the same. If we look at these two alkenes on the right, they are stereoisomers. If you describe the connectivity of the atoms, they are both 5 carbon chains with an alkene between 2 and 3 and a methyl group on carbon 3. That's the same description for both molecules, yet these are different, and that's because spatially the groups are arranged differently around the alkene. You cannot rotate around that double bond, so the two molecules are locked in place around that double bond and cannot rotate from one into the other. If you had free rotation, these would be the same, but it's not the case. So we have cis or trans E and Z configurations. Now for stereoisomers, there are two types of stereoisomers: enantiomers and diastereomers. Diastereomers are stereoisomers that are not mirror images. So when you look at these two alkenes, E and Z alkenes, they are not mirror images. If you take the mirror image of the E stereoisomer, you do not obtain the Z. The Z is not the mirror image of the E. So these are called diastereomers. Enantiomers are stereoisomers. They're not the same because the atoms are arranged spatially in different ways. And two enantiomers would actually be mirror images of one another despite being different. They're different, they're stereoisomers, but they are also mirror images of one another. So we say they're non-superimposable mirror images. So when you look at these 4 compounds, they all have the formula C6H12. If you recall, an alkane with 6 carbons would have 14 hydrogens. C6H14 for an alkane. CnH2n plus 2 is the general formula for an alkane. But these are C6H12, and they all have 2 hydrogens missing compared to an alkane, and the reason is either a double bond or a ring reduces by 2 hydrogens. Now these are all constitutional isomers of one another. They all have the same molecular formula, but they are arranged differently. The connectivity of atoms. We have a 6-membered cycloalkane. We have a 4-membered cycloalkane with 2 methyl groups. We have 2 6-carbon alkenes, straight chain alkenes, but the location of the double bond is different in the chain. So those are all constitutional isomers. Now how about these two? These two are both 2-bromobutane, but they're not the same. They are mirror images that are not identical. So these are stereoisomers, and specifically enantiomers. How about these two? Well, they are both 2-butene, but we have the E and the Z forms. So these are stereoisomers. But are they mirror images of one another? No, they're not. So we call these diastereomers. Now here we have two alkenes. One is E2-butene, and the other is 1-butene. They are not stereoisomers of one another. The location of the double bond is in a different place for each molecule. So these are constitutional isomers. So there are two chiral centers in 2,3-dimethylcyclohexane. We have a cis and trans form of this molecule. Cis 2,3-dimethylcyclohexane and trans 2,3-dimethylcyclohexane. Now, are these two mirror images of one another? No. So these are diastereomers. They're stereoisomers that are not mirror images. These are two stereoisomers. How many stereoisomers are possible? We have two chiral centers. 4 possible stereoisomers. The question here is, do either of these have enantiomers? They're not enantiomers of one another because they are not mirror images. Now, if we take the trans one and we do the mirror image of it, so these are enantiomers. There are actually two different trans versions of this molecule. If you try to rotate one of these and make it identical to its mirror image, you cannot. They're not superimposable. So the trans form does have an enantiomer. Let's look at the cis form. Does this one have an enantiomer? Well, let's draw its mirror image. Are these different? Are they non-superimposable? They are not different. They are actually superimposable. If I rotate one of these around, I get the original. So the mirror image is not different. So this is the meso form. So there are actually 3 stereoisomers because the meso form reduces the number of stereoisomers. So the question was, do either of these have an enantiomer? The original 2 molecules shown in this problem are stereoisomers. They are more specifically diastereomers because they're not mirror images. The trans form does have an enantiomer, another stereoisomer that was not drawn in the original problem. The cis form is a stereoisomer of the two enantiomers, the trans enantiomers. All three of them are a collection of three different stereoisomers. But the cis form itself does not have an enantiomer. Its mirror image is not different. It is what we call the mesoform. So there are three stereoisomers, a pair of trans enantiomers, and a meso enantiomer, the cis form.